Hello, everyone. Welcome to MACSMIN, Mathematics and Computer Science for Materials Innovation. It's a great pleasure to introduce Professor Nikolay Dolbilin from Steklov Mathematical Institute, who will talk about local rules of crystallinity and groups in Delone sets. Over to you, Nikolay Petrovich.
Okay. Dear Vitaly, thank you very much for inviting me at this to participate at your conference, and I hope my poor English will allow to share some details, some ideas of our theory developed in the Steklov Institute during almost half century already, really. Certainly with very strong, with very long break, but anyway, this theory appeared in 1974. Okay, so the topic of my talk relates to the foundations of geometric crystallography. Maybe it has no much applications for practical practice, but for foundations, I believe that it has some very strong value, really. And for instance, in the beginning were Delaunay, Dolbilin, Dolbilin, after that angle joint, Lagarius, Schulte, Seneschal, and so on, people who invented some contribution, made some contribution to this theory. Okay, but may I delete this? How I can delete this?
Cursor.
What this? Okay, so, okay. And the main goal of this theory was, and still is, to explain the appearance of a space group or global order in the atomic structure of crystal in geometric terms of local conditions. Modern crystallography originates in works of René Haï. No, it is funny that, like the story of how a fallen apple led Newton to discover the universal law of gravitation, a calcite crystal crashed during a fall led Haï to the discover three-dimensional periodicity in a crystal. Haï's ideas was fundamentally continued in later the studies of Auguste Bravais. He looked at the lattice not only as a periodic structure in three dimensions, in three directions, but also as a structure that has some other symmetries different from translations, rotations, reflections, the superpositions. The result of his research was the famous classification of the family of lattices into 14 Bravais classes, on the picture on the right. And you see what Fedorov continued this Bravais idea of unifying translational and rotational symmetries of lattices, and it introduced the notion of a space group as a discrete group of isometries of space which has a compact fundamental domain. Fedorov simultaneously with Champlice found complete list of all 230 space groups. And what is very important, Fedorov understood, but Champlice rigorously proved, that any space group has a translational subgroup of finite index. This is a very important theorem because due to this theorem, the class of all possible crystal structure defined by Fedorov, I will explain it later, it didn't really, anyway, it kept periodicity of these crystalline structures in all 3 dimensions. And Fedorov defined regular systems. A regular system is a generalization of the concept of the lattice. Given space group G and a point X, the orbit over this point under action of this group is a regular system. It's called a regular system. Equivalently, a regular system is a Delaunay set in which all points are surrounded by others up to infinity in the same way. Indeed, what this up to infinity, but on the first look, what this definition, the second definition for a regular system, is free from concept of the group, symmetry group. On the other hand, when you precise what does it mean, all points are surrounded by others up to infinity. It means that there is isometry that moves one point to any other point of the system by some isometry which superposes this set onto itself. By Chamfry's theorem, a regular system is a union of the same, of equal, congruent, and parallel each other lattices. But look, please, this is an example of a regular system on plane. It is the group, space group, no, plane groups in this case, two-dimensional crystallographic group. It is a group of square lattice, and the orbit of this point, red point, looks like this, the union of 4 lattices. If you take this point, but my cursor is seen, Vitaly. But
yes, we can see your cursor.
Okay. But if you take this point and this point generates some lattice, what lower points in any quadruple, and one lattice. This is the left points in quadruples form another lattice. Top points and the third lattice, and the right point is the fourth lattice. But so this regular system is a union of 4, in this case, 4 lattices, equal and parallel each other. And this is not randomly. This is a corollary of the theorem I mentioned here. Any space group has translational subgroup of finite index. The theorem which was proved by Chamfry for dimension 3, by Bieberbach for dimension greater than 3, because Hilbert in 1900 he suggested this problem to prove Chamfry's theorem for any dimension. It was one of the famous Hilbert's problem. And Bieberbach in 1912 or 1913, he proved this fact based on the idea of Chamfry. By the way, also Fedorov also, but for dimension 2, it is very trivial to prove this theorem. But for dimension 3, Fedorov believed, he was convinced that the theorem is true. Moreover, he found, as he seemed to me, it seemed to him, he found this proof, but this proof contained a very serious mathematical gap. And really, the first proof of this theorem belongs to Schottens. So, and after that, Fedorov introduced the definition of crystal. Let X0 be a finite point set, some endpoints. And the G orbit of this finite subset X0 is called a crystal. So any crystal, in mathematical definition, by mathematical definition of Fedorov, it is the union of several regular systems. But at this picture we have three regular systems: red, blue, and brown. And on the other hand, any regular system splits into congruent lattices, parallel lattices. So we have 4 red lattices, 1 blue lattice, and 1 brown lattice, 6 altogether. And now we are coming to our local theory. Okay, structure with a space group. Where does it from? Where does it come from? Okay, we have on the left picture, we have liquid amorphous structure, water, for instance. On the right, we have a crystal, an ice, for instance. And we have in the middle, we have something, what is going on under transition, under fast transition, under freezing of this liquid. And why during crystallization do atoms combine into regular systems? That is, into structures with crystallography groups of symmetries. Indeed, the atoms do not know what a symmetry group is. Okay, similar question, the equivalent question. Why during crystallization do atoms try to surround themselves identically up to infinity? In fact, during crystallizations, atoms interact only with nearby atoms, and we can do only assume in the crystal the coincidence of the nearest environments around each atom of the same kind. But these questions were in the center of our attention in 1974, when we worked with Boris Delaunay. The first attempt to explain geometric shapes of crystals in terms of the patterns and of the constituent particles was done in the essay by Johann Kepler in the hexagonal snowflake. In this famous essay, also Kepler stated a problem. Not a problem, he made a conjecture. The densest pattern of 3-dimensional space with equal balls is the FCC, phase center cubic lattice. And this problem, this conjecture, in fact, this conjecture was said to Kepler by his friend and mathematician Thomas Harriot, but Kepler in his essay didn't mention this name. And this conjecture is now well known as the Kepler conjecture. It was solved only in 1999 by Thomas Hales, United States. And so Kepler's argument is in favor of the periodicity of the structure, which occurs during crystallization, was the densest packing principle. Atoms during crystallization attracting each other tend to fill space as densely as possible. And this automatically leads the structure to the hexagonal lattice in the two-dimensional plane, because two-dimensional hexagonal lattice two-dimensional plane is obviously the densest packing. And in three-dimensional space, it is a face-centered cubic lattice in space. And really monatomic crystals, for instance, metals, cuprium, and so on, obey this Kepler's principle and used to form dense packing structures. However, molecular structures are not always so dense. For instance, silicates have really porous atomic structure, and water under freezing even expands them. And so the densest packing principle under crystallization, during crystallization, doesn't work for about 80% minerals existing on Earth, including for silicates. And another principle was expressed, the energy minimum principle was expressed explicitly by Richard Feynman in his lectures on physics. When the atoms of matter are not moving around very much, they get stuck together and arrange themselves in a configuration with as low energy as possible. If the atoms in a certain place have found a pattern which seems to be a low energy, then the atoms somewhere else will probably make the same arrangement. For these reasons, we have in a solid material a repetitive pattern of atoms. And the environment of a particular atom in a crystal has a certain arrangement. If you look at the same kind of an atom at another place, or farther along, you will find one whose surroundings are exactly the same. And if you pick up an atom farther along and by the same distance, you will find the conditions exactly the same once more, over and over again. The pattern is repeated over and over again, and of course in three dimensions. So this is a very plausible paradigm, but really, certainly, if you look, for instance, Penrose Stalin, each local, look please, here Penrose is standing at Penrose patterns. It was in Texas Mining University in Texas College Station. I have been there and I saw this hole. Exactly, it looks like here. And look, please, for instance, for this pattern of Penrose pattern, and look, please, on the vertices of these rhombuses. There are two kinds of rhombuses, red, black here, and gray, thin rhombus. And their vertices form Delaunay sets in which local fragments are repeated over and over again. And nevertheless, as well known, Penrose pattern has no any periodicity, has no any other symmetry, global symmetry, except for in one explicit case when there is one global symmetry, five-gonal symmetry, but it is only one pattern among uncountably many other patterns. It is very interesting point. And so, in fact, the minimum energy principle sounds very natural. Nevertheless, until 1974, no general formulation of local conditions for regularity of a discrete structure was known yet. And the central aim of local theory was to find a correct wording of local conditions, providing the appearance of space group. And certainly, we as mathematicians had to rigorously prove this this correct wording. And the theory was started in Delaunay groups in Steklov Institute in 1974. And at the very end of this year, maybe 2 or 3 months after that, it will be found with one of the central results of the theory was found. Okay, but here Boris Delaunay on this picture, he is preparing for a hike. You see what condition this picture was taken in 1973 at the same time when we started this local theory. At first, we started with a series of very natural questions on tilings of space. What, for instance, you have monahedral tiling on plane. On plane, monahedral tiling means that tiling with congruent polygons. All polygons are the same. Okay. Can you guarantee that that regular polygons congruent polygons, for instance, triangles, can tile space by only with crystallography group or in isahedral way. Isahedral tiling means polymonahedral tiling with congruent tiles and with the symmetry group operating on this monahedral tiling tile transitive way. Any tile can be moved to another tile together with the whole tiling. Okay, certainly no. The answer is no. Whether tiling with congruent first corona is isahedral? No, also. Who knows? But for instance, I remember when what first idea came to my mind. I remember even the day of this event, and it was the following: let's your tiles in monahedral tiling is asymmetric. It has no any symmetry. For instance, like in a regular triangle. And assume your tiling with this triangle is such that also first coronas, the closest, the neighbors along sides, also are the same for each triangle. Then it is very easy to see, but it was surprising, by the way. It was easily to see that this tiling is necessary isahedral tiling. And after that, in 1 week from that discovery, and we found the local criterion for isahedral tilings. But so Delaunay suggested to reformulate this result in language of point R, small r, capital systems. These systems is the set points placed in space and satisfying very natural conditions. We will talk about this a little bit later. Delaunay introduced the concept in this small capital systems in 1934, and since then it has become an appropriate model for atomic structure, regardless of whether it is crystalline or amorphous. Since the late 1980s, RR systems are called Delaunay sets. What is a Delaunay set? in any dimensional Euclidean space RD. If for some positive numbers are small and are capital, open both with radius are small, centered at points x, do not intersect each other. So what they don't intersect. And the closed balls on another side with radius r cover the whole space ID without any gaps. And condition condition R small is what this condition are equivalent to the following: distance between any 2 points of Delaunay is greater or equal to than greater or equal than to R. Conditions are capital is equivalent to the following: distance from arbitrary point of space, not only of space of x, of arbitrary point of space to the nearest point of x doesn't exceed R capital. And what, for instance, example is Delaunay set is a set of red points. They form a rectangular lattice based on the basis A, coordinated 2, 0, and B, 1, 0, 1, what here, and rectangular pattern, rectangular lattice. It is easy to see that R small for this case is half, and R capital square root. R capital is this one, what this, and its radius, it is equal to square root over 2. Okay. So a regular system is a Delaunay set with a transitive group, and for any x and y, there is isommetry G, such that Gx is equal to y, and Gx and x moves into the set x, moves into itself. Any regular system, I repeat here again, is the finite number of lattices. And now, okay, the cluster. The cluster, let us given row, positive number row cluster at point x is a subset of points x prime which are remoted from x at distance not exceeding rho. And for instance, if you take as rho is equal to R small, then you have what this cluster. Cluster with radius smaller than 2R is consists of the single point, and all clusters are congruent between them. All clusters of radius rho, where rho is smaller than 2R, consist of the single point. And on the other hand, what this is a cluster of the radius 2R, it is very essential value of radius 2R, because but now the definition. Given x and fixed number rho, two clusters of the same radius rho at point x and then point x prime are thought equivalent or congruent if there exists isometry that moves x to x prime and the cluster to the cluster. What it superposes then for a given Delaunay set, for any row, there is some number of equivalence classes of row classes, because we don't assume that all classes have to be congruent, have to be equal. They can be different in the arbitrary Delaunay set. And but if X is a regular, then the number, all clusters of any fixed radius row are pairwise congruent. And the number of this function n of row is identically equal to 1 for any positive row. If X is a crystal, more general system, then n of row is doesn't exceed some natural number m, which is finite positive number. And this number m is the number of regular systems in the crystal. And the row is called the cluster counting function or complexity function. And the n of row is one for any Delaunay set, absolutely arbitrary, is one for small row. N of row is finite, but for a bigger row, n of row can be, for if you take absolutely arbitrary Delaunay set, then n of row complexity can be even infinite. But if it is finite, n of row, it is finite for the value to r. So in other words, assume in our Delaunay set, the number of different 2R clusters is finite. R capital, 2R capital clusters is finite. Then it is finite, but this number, it is finite for any radius row bigger than 2R. On the other hand, what this function is defined, in this case, is defined and monotonically doesn't decrease. It usually it is increasing, but maybe it can be remain constant when as a row grows to infinity. So the definition, the cluster group is the group of all isometries of this cluster. As X is moving to X, and this one to this one, and the cluster into itself. And okay, what this group F X of rho, when rho is very small, then for instance, smaller than 2R, then the cluster consists of the single point X, and the group of symmetries is infinite. It is it coincides with how to say orthogonal group at the point X. But when X rho is growing, then our group becomes smaller, and when rho becomes 2R capital, then this finite group, this Fx of 2R is necessarily finite. This is a very, because the 2R cluster is always of rank D, full dimensional D, and the finite point set of rank D have only finite group of symmetries, not infinite. And so what we have, for if rho is growing, then our group, or excuse me, cluster is growing. Certainly, this bigger cluster contains a smaller cluster, but the group, corresponding groups, can only decrease or remain themselves, remain the same. And the cluster groups, generally speaking, differ. So, but it is very important. They differ. They differ from the point group of the whole space of the whole set Sx of infinity, and so the cluster group can be much bigger. And group acting on the limited clusters are of special interest. It is Alan McKay emphasized this fact, and because they may be non-crystallographic even in crystalline structure. And on the other hand, they can be seen on diffractograms, and because of this, they can give you some false representation of the global finity of this group, because local groups can be richer than the global group. The behavior of cluster groups plays an important role in the local theorem of regular systems. And now, regular system is the basic component of any crystal, ideal crystal. For any given row up to infinity in a regular system, all clusters are pairwise equivalent. It is obvious. And my question, is there some value rho zero such that if in a Delaunay set X, all small clusters of radius rho zero are pairwise the same, but then for any row bigger than rho zero, are also the same, and consequently the Delaunay set is a regular system. This is the main question, and the local criterion gives the answer to this question. Given Delaunay set X, let for some rho zero two conditions hold. First, for all points, clusters of this radius rho zero plus 2r capital are pairwise equivalent. And the groups, but this is very important, the groups of cluster rho zero and the cluster of rho zero plus 2r are the same. Then Delaunay set is a regular system. Moreover, it is obvious that it is true for in opposite direction. If the regular system, if the X is a regular system, then these conditions fulfill for some rho zero. So this is the local criterion. And from this criterion, by the way, it follows the following. Assume our two are cluster, but assume we have a Delaunay set in which all, I'm sorry, I have how much time I have? 15 minutes. Vitaly?
About 10 minutes.
About 10 minutes, okay. So, so by condition one, any two points X and X prime, for any 2 points, there is an isometry G which moves X to X prime and combines the cluster this one with the cluster this one at the point X prime. By local criterion, this isometry, what this is very important, this isometry moves also the whole set X into itself. This is the point of this local criterion. And from local criterion follows that for any dimension D, there is some constant phi dependent on the ratio R capital over R small and D, such that if in Delaunay set all clusters of this radius are pairwise equivalent, then X is regular. And what is the regularity? Regularity radius rho D for dimension D is considered like the minimal radius of clusters whose pairwise equivalent provides a Delaunay set X to be a regular system. And for dimension D, for plane, this regulated radius is equal to 4r, not lesser, or 2 for r. For dimension 3, it was done by Dolbilin and Stockton, and in last year we wrote a long paper proving this fact and developing this fact further. I will mention this one page later. The D equals 3, three-dimensional space. It is bigger than 6D and lesser than 10R. 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 It was done in my work, 2018, and one group was missed here, and in this joint paper we completed this gap and wrote a very extended exposition of this bound. A low bound for dimension D. It is but for me it was a little bit surprising that for any dimension D, but the low bound for a regulated radius cannot be lesser than 2dr. So 2dr is the radius if you if you take the if you require the pairwise congruence of a lesser radius than 2d times r, then you can find a Delaunay set with pairwise equivalent clusters, but the Delaunay set is not a regular set. So smaller values are not enough for regularity. And also, what the dimension 4, dimension 2, I'm sorry, given Delaunay set, if all 2R clusters are equivalent, then equivalent, and the group of symmetries is not trivial, so 2R cluster has at least one non-trivial symmetry, then X is a regular system. But if this SXR to R is trivial, then one needs to require equivalence of clusters of bigger radius 4 times R, and in order to provide regularity of the system. For any epsilon, positive epsilon, there is a Delaunay set such that what these clusters are of radius 4r minus epsilon r pairwise equivalent, but the system is not regular. Okay, yeah, I think I will miss this one. The plan of the proof of the three-dimensional case, and also pay attention to this, in my opinion, very important remark, theorem, the following theorem. Assume, this theorem is true for any dimension. Assume X is a Delaunay set in which all 2R clusters are pairwise congruent, and the local group contains the central symmetry sigma. Then X is a regular system. So the central symmetricity of local clusters of radius 2R and congruence of such clusters provides regularity of the whole system. And for dimension D equals 3, it has a very good contribution to the proof of this I'm sorry, estimate 10R because we 14 groups from some list which is has to be considered for our problem. 14 groups automatically contain the symmetry group, and this implies that any two isometrical Delaunay sets with such local groups from the number of 14 is a regular system. And this is the following theorem works for any dimension, by the way. It is very interesting. But here we don't require anything about from Delaunay set except that all 2R classes are central symmetrical. They can be different. They can be even the number of clusters can be, how to say, infinitely many classes. Nevertheless, if all clusters are central symmetrically, then X is the union of not greater than 2D minus 1 congruent and parallel each other lattices. So X is the number, is the union of this lambda and the in translational images of this lambda in the number of 2 to the D minus 1. This is so our cluster, our Delaunay set is a crystal. And but here in the local theory of regular systems, we assume the pervasive identity of classes of the same of some radius, at least 2R. Recently, we found some interesting facts on general Delaunay sets, which imply something important for regular systems. So we we consider arbitrary Delaunay set denoted by X tilde, subset of all points X from X, such that the order of any rotation from the local group at this point doesn't exceed 6. And the subset of a Delaunay set X is a Delaunay set with some covering radius ρ tilde bigger than ρ. And from this theorem, for instance, the Stockton's lemma, which was important for 2 isometrical Delaunay sets in three-dimensional space, follows immediately. And what here, the estimate was covering radius ρ tilde of the subset X has been clarified. For X, let X is a Delaunay set with covering radius ρ, R capital. Then the covering radius of this subset X tilde is smaller than 3R. And now, what here, the crystal kernel. We introduce the idea of a special subset, which principle has to be in an arbitrary Delaunay set in dimension 2 or 3, given Delaunay set. We call a subset of all points whose local groups contain only rotations of crystallographic orders, that is, of 2, 3, 4, 6, but not 5, 7, 8, and so on. Define this subset the crystal kernel. Denote the crystal kernel by this X sub, this notation. Certainly, X, what this kernel, crystal kernel, is contained in X tilde, because X tilde is contained in X, because we removed from X all points at which local groups contains no points with local axis bigger than 6, order 6. Here we remove from all these points, we remove points which have no axis of order 5, and we get a kernel order. And in X, let X be a Delaunay set on a plane with a covering radius R. Then its kernel, its kernel is a Delaunay set with a covering radius such that where this radius doesn't exceed to R, where R is radius covering of the point is original point X. Here estimate is exact, by the way. And moreover, any Delaunay cell of the Delaunay tiling contains at least one vertex in the X crystal. What this last statement implies this fact, this estimate as well. It is very interesting fact, unfortunately proved only for dimension 2. But anyway, even for dimension 2, it is, for instance, it generalized much, it strongly generalized what famous theorem on the prohibited excess of 5 of the order 5. What you remember yesterday, Marjorie said that in the two-dimensional lattice there is no five-fold excess, five-fold symmetry. But look please at this theorem. Let X be a R2 isometrical set on plane. Then the local group X to R contains no five-fold rotation. And it is this theorem immediately follows from what this one. And but now look please at this theorem. It generalizes the celebrated fact into the lattices there is no five-fold rotation, and it generalizes in two directions at once. First, this theorem is true for much bigger class of Delaunay sets, not only for lattices, but for because lattices is a particular case of regular systems. Regular systems is a particular case of two isometrical sets. So this theorem is true for the two isometrical sets. First. Second, it generalizes in another direction. Marjorie said about global symmetry, but global symmetry, that five-fold rotation, cannot be a global symmetry of a lattice. But we are talking about local symmetry. Our local symmetry could be, could have five-fold lattice. Why not? So this is another direction of this generalization. But as for dimension 3, this theorem is not proved yet, and for three-dimensional space, for instance, there is a regular system X such that local groups of clusters of radius R3. What does it mean, R3? What we have in our Delaunay set, for instance, we have the first minimum, we have the second minimum, we have the third minimum, and if you take and the radius R1, the radius R2, the radius R3, what the cluster of such radius of radius R3, even they can have the group of order 5 in three-dimensional case, and this is a regular system. Certainly, the regular system cannot have global rotation of the order 5. cannot have regular systems because regular systems consist of three-dimensional lattices. But but the local groups can have this five-dimensional axis, five-fold axis. And nevertheless, we suggest that for any dimension set X, the crystal kernel X, the crystal kernel of this set X is also a Delaunay set. And from this, it follows the same theorem. From this conjecture, it follows the same theorem which generalizes five-fold symmetry in lattice up to much wider class of Delaunay sets. Thank you for your attention.
Thank you very much, Nikolay Petrovich. So please thank Nikolay Petrovich physically or virtually. I'm stopping the recording, and